Hello and good afternoon friends, welcome once again to the CEC EduSet live lecture. Dear friends, as you know that in our previous sessions we discussed on lexical analysis, syntax analysis, as well as we talked on semantic analysis. Dear friends, we would be talking on semantic analysis more as this is the continuation with the previous lecture on semantic analysis, and for this we have again with us in our studios Mr. Sarfaraz Masood. He is Assistant Professor in Department of Computer Engineering, Jamia Millia University. So first of all, I would like to welcome our guest, Mr. Sarfaraz Masood, and we would be talking more on semantic analysis. Welcome to the EduSet lecture, sir.
Thank you.
So over to you, sir.
Thank you once again for calling me over here. Good afternoon, friends. Once again, we continue our discussion on compiler design. In this today's lecture, we would like to go on with semantic analysis. We had one lecture on this topic earlier as well. And in that lecture, we talked about the basics and the initials of semantic analysis. So in today's lecture, we'll quickly recap and review those points, and then we'll move on with today's objectives. Just to remind ourselves with what we have done, an overview of syntax-directed translations and syntax-directed definitions, translation schemes. We also talked about the annotated parse tree concept, and we concluded that lecture by talking about dependency graph. So this was all about extracting meanings. Actually, this is all about semantics, taking out meanings from the different parts of the program that we have given, which has been checked as far as lexically is concerned, and syntax analysis has also progressed by now. In today's lecture, we'll try and understand the construction of syntax trees. Definitely, we'll try and more understand about syntax tree, their construction. In short way, I would like to say that we would like to know more about the process of writing rules for construction of syntax trees. S attributed and L attributed grammars and definitions. We'll also like to know something about evaluation of semantic rules, because this is something that ultimately has to happen. Just by writing semantic rules is not going to help us quite much. And then we'll definitely put forth some constructive remarks. I deeply acknowledge the various sources from which the examples and images have been used for the purposes of lecture, specifically the Ahol Mansuri book that we have been referring for the lectures till now. Okay, so we talked about this part in that very slide also. This is the syntax analyzer, the parser, and why I am having this slide once again was the fact that syntax analyzer was also having with it the parser. Along with the parser, there was translation rules also embedded within that. So it means that in this very slide, in the last session as well, we talked about the fact that the parser is not the parser alone now. It's now a combination of parser as well as the semantic analyzer also. So the translation rules are also usually hard coded within the parser. That's why we get the abstract syntax trees and the syntax trees in bytecode and assembly code, whatever we want. So the output that we are getting in a different format actually is nothing but because of these translation rules which are actively running along with the parser. So we have already talked about the kind of parser, the LR parser and the LL parsers. So we continued with this concept. And just to remind you the way these definitions and rules were written. So if you talked about just the syntax directed definition, I've already discussed what these are all about. So this example also we have discussed in the last class, in the last session I mean. L derives E, N, E derives E plus T, E derives T, and on the right hand side we can see that we are having the semantic rules over here. So what we expect from this production, I mean what meaning do we want to extract, has been written over here, has been prescribed over here. So this is actually one thing more I discussed in the last class and in the last lecture, is that this meaning that we have written over here is the one that we want. Okay, so it's not, I mean it's written E derive E plus T, so that is why we written E dot val is equal to E1 dot val plus T dot val. It's actually this meaning what we want to extract. This is the reason why we've written a rule of this type. We want the attribute value obtained till here and the attribute value obtained till here to be added and then passed on to this E. So this was the way we had written, this was the way we wanted the meaning. So this is the very way we have written the rules. So the meaning what we want is the way we write the rules. So that's a very simple way of understanding the concept. So all these rules have been written over here, keeping in mind the kind of meaning that we want to extract from this set. And I think we also went across this annotated parse tree for this sentence 4 minus 6 by 2n, and we can see that this is a valid parse tree or a derivation tree from this very grammar. And I also discussed about how these values are being traversed. So this was all about extracting meaning. This was all about getting those semantics from the sentences. But in order to get the meaning of the sentence, rather than going to the sentence, it's better that we look into the grammar that we have given. That is why this all content is referred as to syntax directed definitions and translation schemes. All the meaning extraction process has been directed by the syntax or the grammar. Okay, so we left at this point that we knew how the semantic rules are to be written for a certain fact. So if we know our task, that this is what we want to perform, then writing the semantic rule will not be much of a challenge. Our task should be clear, and the grammar should be valid enough. So how to get a syntax tree out of this grammar of ours? So if, let's say, we are given a sentence, and for that sentence we want a syntax tree, then how the syntax tree will be generated? Because the parser is not constructing the syntax tree. The parser in technical terms is just checking whether this sentence is valid as far as the grammar is concerned or not. The task of generation of the syntax tree will be done by the semantic analyzer only. So what's a syntax tree actually? It's a tree, this one is a reduced or a condensed parse tree, where the operators and the keywords are the interior nodes, and the operands and the non-keywords are the leaf nodes. So if you're not talking in terms of an expression tree, so this is a very valid kind of a definition for it. So it's a reduced or a condensed form. So you can see over here, it's a pretty large kind of a structure, and this one is a pretty simple one. So it's a condensed form. For example, although this is not the example for the previous slide I was showing you, this example parse tree syntax tree is for this example. S derives if E, if B, then S1, else S2. So it was saying that where the operators and the keywords are the interior nodes. So we're not having any operators over here, we're simply having the keywords. So keywords are if, then, else. Let's say if they are the keywords of a certain language, then you can see them to be the interior nodes. Whereas these variables and or I would say the non-keywords are the leaf nodes. So the non-keywords are this B, S1, S2. These are the non-keywords. So we can see them to be as the leaf nodes. So this tree would not be called a parse tree. Rather, it's actually the syntax tree. So this is actually giving us the information about the sentence only. Just to give an example about a sentence from the previous grammar, the E derive E plus T grammar. So 3 plus 3 star 2. So if you just try to make a parse tree of it, you can see that this is the parse tree. This tree is telling us more about how this sentence is syntactically correct, whereas this is a much more condensed form of it. It's simply telling us the way this sentence is structured. So this is like 3 plus, that means this operation has been kept separately and will be performed separately. 3 plus 3 into 2, this operation will result something over here, and these two will be added. So this is more kind of a hierarchy of the sentence itself. A syntax tree allows the translation process to be separated from the parsing process. Actually, a grammar that is best suited for parsing might not be explicitly exhibiting the hierarchical nature of the programs it describes. This is pretty much valid. The parsing method imposes an order in which the nodes are considered, which might not be the best for translation. So the parsing, I mean, the grammar is telling you that how this thing would be structured actually, but that does not tell you that how will it mean, as we can see the case over here. This is telling us that how this will be structured. I mean, if we are trying to go by the rules kind of a scenario, then this is how we are getting 3 plus 3 star 2. But what does it mean? I mean, which of the two components are together without any clutterness of all these variables and terminals? I mean, the meaning of this could have been 3 plus 3 into 2. But if this is the kind of the meaning we want, then we'll have to specifically describe it by the help of the syntax tree. It's not having any extra information like E and T and F and all those variables, nothing. It's simply telling you that this is the sentence and this is all containing the components of the sentence only, no extra symbols, and it is very much telling you how or what will it mean. So if we more talk about the meaning part, then it's more exhibited by this rather than being exhibited by this. So this is what it's saying, that the parsing method which imposes an order, definitely we are all talking about order in syntax analysis or hierarchical analysis. So this is the order in which the nodes are to be considered. This is the way these nodes should come. This is the way these elements should appear, which might not be the best for translation, but this is not the very way in which they might mean something. As we all know, the case of for loop or let's say any example in for loop, we have initialization, then this is followed by a condition, this is followed by an increment, decrement, and then it is followed by the body of the loop. However, the meaning is actually something different. As far as the meaning is concerned, or the actual running of the loop is concerned, the initialization is followed by the condition, and then the entire increment decrement part is kept at this level and the body is executed, and then after the execution of the body, the increment decrement part is to be executed. So we can see that the way it has been structured does not mean that this is the very way it should mean. I mean, this is the very way it should make some sense. So the way it should be translated can be different by the way it has been ordered. Constructing syntax tree, use a syntax directed definition to create a syntax tree. So we'll actually write a syntax directed definition, and we'll try and see how this definition will result in construction of a syntax tree. Each node can be represented as simple data structure. Operator structures will have a name and a number of fields containing pointers to each operand. Simple operand structures will have a type and a value. For example, 2 plus 3, and the syntax tree would something look like this. So we're just having the operands as the leaf elements and the operators as the node elements or the interior elements, and these operands are actually having some extra informations also, which was being talked about, which are actually nothing but pointers to the operands. Yeah? Number of fields containing pointers to the operand. So this is the operator structure and this is the operand structure. It is having the value as well as the pointer to the operands, and this is simply having the type and a value kind of a thing. So if this was a task given to us, I mean, let's analyze first of all this part. Then in this entire syntax tree, what we are getting are interior nodes and leaf nodes. And if I talk about if I strictly talk about an expression tree, let's say we are constructing a syntax tree that will only have expressions, then in that case we'll see that the interior nodes will always be kind of a binary kind of a structure. Binary, I mean, it will be having 2 child, whereas the leaf node will not have any other further children in it. It will be a kind of an end point to it. So two kind of functions we'll need. We'll need one function that will build this kind of a node, and we'll need a function that will build this kind of a node. Okay, so we'll have a make node function, and we'll call that function at the appropriate time in the grammar, in the semantic definition, and we'll have this function called make leaf function, which will be called appropriately at a different point. So 2 different functions we'll have. In fact, we'll have 3 different functions as far as the structure, the syntax is concerned. It's saying make node function will be there. The first element of it will be an operation, followed by the left child. That's the pointer to the left child and the pointer to the right child. It says creates an internal node for the operator op with 2 fields for the pointer to the left and right operands. Make leaf id actually is actually a function that creates a leaf node of an identifier. Creates a leaf node for an identifier id and the field for an operator for a pointer to the symbol table in the for the entry of the identifier. Make leaf num actually is a leaf node that is to be constructed for a number. So creates a leaf node labeled num with a field for a value of a number or constant actually. Each function returns a pointer to the node just created. So we'll use any of these functions, any of these three functions at the appropriate time, and then this function, once called, it will return a pointer to that node. So by doing so, we'll keep on creating some nodes, and we'll keep on attaching them, and ultimately we'll have the pointer to the root node, which will be nothing but the entire syntax tree. So let's look again at this grammar. So it's the same grammar, E drive E plus T, but now the semantic or the meaning that we want to extract from this grammar is not the value. In this case, the semantic or the meaning that we want to extract from this grammar is generation of a syntax tree. So we expect a syntax tree from this grammar. So on the same grammar, we are writing a different set of semantic rules and we are generating something else of it. So that was the idea of semantic analysis, that from the same grammar you want a different semantic, you don't want a different meaning, write a semantic rule or write a definition for it. So if you want type, write semantic rule for it. If you want value, write semantic rule for it. So we will have to write definition for it. If you want syntax tree, write semantic rule for it. You want parse tree, write a semantic rule for it. So for each meaning that we want to extract from this grammar, we'll have a set of semantic rules or a definition for that very purpose. So syntax tree is an intermediate representation of compiler's input, employment of synthesized attribute NPT. So we are taking an attribute NPTR, and if I remember, we have also discussed about this synthesized attribute and inherited attribute. Just to recall that, synthesized attributes are those attributes are actually the attribute of the parent in a subtree, whose value actually depends upon the attribute value of its children, whereas inherited attribute is that attribute whose value actually depends upon its sibling or sibling's attribute, or it depends upon the attribute value of its parent. So in that case it will be inherited. So in our case, actually right now we are talking about an NPTR attribute, which is actually containing nothing but the pointer value, and this NPTR is a synthesized attribute. If we imagine ourselves to be looking at a syntax tree, then in that, or a subtree actually, then this NPTR is the pointer of this NPTR is the attribute of the parent, and its value is actually coming or dependent upon its children. So let's look at this individually. As I would go again with my statement that look at the meaning that you want. The meaning that you want is the very same way or the very way you have to write the rules for it. So this is E drive E plus T. So if this is the node in my parse tree or in my derivation, then what do I expect from it? So E will be definitely an interior node, of the parse tree. T will also be an interior node of the parse tree, and then these two will be combined together to form the E or the parent. So at this very level, what meaning do I want actually? So I would be getting a connection to this, I would be getting a connection to this, and these two connections have combined together, and the op has been given to me. This is plus. So if I make an interior node in my syntax tree such that this is the operation, this means the left child, and this means the right child, would actually nothing but a stepping stone towards creating construction of the syntax tree of this entire question or any sentence written from this grammar. So the very same way the rule has been written. Rule says E dot NPTR, that means a pointer to this node or an attribute that will be containing a pointer value, will be actually nothing but call this function make node, the one we called the one we were talking about over here, and give it the first operation. This is the operator part, and this actually will recursively make a pointer to this node as well. So it says E1 dot NPTR and T dot NPTR. These three things kept together, the make node function will create an interior node, and its pointer will be passed on to this and will be kept in this attribute E. So this is the meaning what we wanted. If we look at this syntax, if we look at this tree, now look what do we want over here? This E, whatever value is coming over here, ultimately this is forming, or if I look at this very part, E drive E plus T, this definitely will form an interior node. So that is why I'm calling this make node function for it. I'm not calling the make leaf function for it. Imagine about this situation. Let's say this would always be nothing but a leaf situation. This will always be a leaf situation. This will always be a leaf situation. But if I talk about T drive T star F, this can never be a leaf situation. This production, whenever called or whenever used, will actually be referring to an interior node. This will never be referring to a leaf node. So depending upon what kind of what production I'm having and what meaning I want to associate with it, the similar kind of or a corresponding kind of a rule is being activated or executed. So I will try and see what answer do I expect from here. So this is a case of constructing a interior node. This is a case of constructing an interior node. This is a case of constructing a leaf node. this is a case of constructing a leaf node. So you can see over here, a make node function has been called, a make node function has been called. However, a make leaf function has been called over here. T derives ID. I'm going back to the same slide. Something like T derives, I mean in this case T derives and F derives ID is the case. But if let's say it would have been T derives ID, then this is definitely a leaf node kind of a case. So this first part is actually the identifier, A, B, result, sum, whatever it is, the identifier part, comma, the pointer to that lexical, to the table actually, to the symbol table. That's the entry of this identifier in that symbol table. And if I am having T derives num, that means I am directly pointing to a number. So I will make a leaf node that is actually nothing but the num, and this will be having num, and num refers to this fact that the value being followed is actually nothing but the number itself. So ID comma the pointer and num comma the number value. So this is how I'm just constructing the leaf node and the interior node. So depending upon what production I'm encountering and what meaning I want to associate with that, I'm calling the right kind of functions. If we look carefully at these nodes, let's say E derives T and T derives E, we do not expect a new node to be created over here because no new value is being generated. So E derives T, I simply say do not create any node over here. Whatever pointer you have got till T, simply pass on to E. So if we look again, E derives T, this is the case. So there's no need to create a node for this very purpose. Just simply collapse this and transfer this pointer to this. So that is why if you look carefully, this 3 comes over here. However, this 3 is actually synonymous to this E, but ultimately whatever value was being transferred to here has been transferred here. So this 3 we have got directly. So there's no need to create any node over here, no need to create any node over this case. That is why no node is being created. Similarly, for this case, T derives within brackets, within parentheses, we have written E. So again, in this case, there is no need to write, there is no need to create any node. Whatever value is coming, let's say 2 is coming from the leaf, we put that within the parentheses. That does not mean that the value 2 has changed. So no new value is being generated. There is no point to create any interior node for it or a leaf node either for it. So whatever node has been created and attached to E, simply pass that pointer value to T and keep it in its attribute n.ptr. So we are just calling the right semantic rules at the right time, and these semantic rules have been written the way we want these portions to mean. So if we go by the same logic that we have discussed till now, this is A minus 4 plus C. So you can see over here, this is if we let's say we go by the left to right analysis, then this operation refers to the plus part and this operation refers to the minus part. So and we are having the left child and the right child. So we get this as A minus, this is the left child, right child is 4. So this node now actually is referring to A minus 4. And this will become the left child for this part. Over here we will be having the plus, and the right child for this will be C. So this becomes A minus 4 plus C. Just taking another example, 6 plus 2 in star 6. 6 plus 2 star 6, that's another case if we talk about. In this grammar we have not talked, I mean in this grammar we have not written something about star or divide, but we can add these rules and the corresponding semantics of construction of syntax tree will be similar. So E derives E plus T, E derives T. So if we look over here, it says E dot ptr, E dot pointer or nptr, whatever we take about. This is nothing but E derive, if we look at this portion, E derive E plus T, then at this portion, what production is being applied, what semantic rule should run? E derive E plus T, that make a node for this, make a pointer for this, and make a node for this, and then attach it in this fashion. So this actually calls the pointer construction for this, which calls the pointer construction for this, which calls the pointer construction for this, and F derives 6. So at this very point, the first node is created, and that node will be num 6. So it is actually referring to a leaf node being constructed with the number 6. and whatever pointer has been generated over here will be passed on to this, will be passed on to this. So at this point I'll be actually indirectly referring to this very pointer, this very node only that represents this. And the right part of it, the t, will again call its left child to be called first or made first, which will ask f to be made first, and f derives 2. So over this case, f derives id will construct a leaf node. So we are constructing a leaf node again over here, and we are passing this pointer to this. No need to create a node over here. We pass on this pointer to this, and this now has a value. Now next we calculate this, f derives id, and this is also constructed. So we create another node for it. This time it's an identifier node, and this mark refers to the pointer to this to the symbol table, and then we combine them as the way the rule was said. So we are having 2 interior nodes. Look, 2 operations, 2 interior nodes, 3 operands and 3 leaf nodes, and then we have the syntax tree. Okay, so the better part of syntax tree can be something called a directed acyclic graph, a DAG. These are definitely advantageous as far as the case of these are concerned. I mean, if let's say we want to have an optimal kind of situation, let's consider this case. You'll understand what I'm trying to convey. A plus A star B minus C plus B minus C star D. So if you try and construct its syntax tree, it will look something like this. Okay, but we can see that this B minus C and B minus C are being evaluated twice. So you have 2 times their nodes in the tree. Ultimately, you'll have both of them in the later part of the construction of the target code. So there's no need of this part. If let's say we would have been having a directed acyclic graph, then one of the occurrence could have been eliminated. Let's say we do not have this part, and we could have connected this to this. So for B minus C would have had 2 parents actually, a star and star over here. This is what I'm trying to say. So B minus C, no need to create this B minus C again and again, connected to this star and connected to this star. So ideally a tree has actually, each child actually has only one node, one parent node. But in a directed acyclic graph, a tree, a child can have, at least one child will have more than one parent node. As in this case, we can see this minus is having this star as well as this star as its parent. Had it been a syntax tree, each leaf or each node will have only one parent. This is having only one parent, this is having only one parent, one parent, one parent, one parent. But by doing so, with the same number of operands, we are having now a reduced kind of a tree, which is actually now not again and again calculating, but only pointing to certain values. So in this kind of a structure, there's no need to create multiple leaf nodes. We can refer, not even a leaf, even interior nodes, no need to create multiple interior or leaf nodes. We can simply refer them by at different locations. Definitely this is better because having this kind of a syntax tree, if we move forward and if we create the target code for this tree, then in this case it will not calculate it will not construct a corresponding target code twice for B minus C. Now it is only being said calculate them once and refer them over here as well as over here. So as a right child to this and a left child to this, just refer them. There's no need to create again and again. So by doing so, the target code gets optimized. So DAG is a very good way to optimize your code, but definitely construction of a DAG is a cost on to you. So how should we modify our definition for syntax trees so that we can produce DAGs now? So all we need to do is actually check. There should be a check at each level before creating a leaf node or an interior node. Has this node been created earlier as well? This is a simple thing that we need to do. If it has been constructed earlier, no need to create again, just refer to that. But this concept of checking at each construction of a new node is an added overhead, is an added cost to this entire process of construction of DAGs. Definitely the end result is better, but it has its cost. So this is what it's saying. Change the make node and make leaf to create new nodes only when needed. So when needed mean if it has been created, better to refer to that rather than creating your own nodes. So in simple way, it's saying first they should search whether one node with the same exact property, that is label, pointer, children, has already been defined or not. If defined, then node must be reused. If not defined, then a new node should be created. but just imagine about the fact that this has to be done for each new node creation. So if you are having, let's say, 10 nodes to be created, with every new node being added to the list, you'll have to do all those n-1 comparisons. So that's definitely a cost, but this is one-time cost. Once the target has been generated, that target will give you benefits for a longer period. Okay, so we move on to a different topic. This is now some attributed definition concepts. There are two types of attributed definition: the S attributed definition and L attributed definition. Syntax directed definitions are used to specify syntax directed translations. To develop a translator, definitely for any arbitrary syntax directed definition can be a challenging task. So it is preferable to evaluate the semantic rules during parsing. So things are changing now. The reason why we gave that first slide, and within that yellow box we said this parser as well as the syntax and semantic analyzer have been kept together. The translations rules have been embedded or hard coded within that. So this point is actually talking about the same thing. It is preferable to evaluate the semantic rules during parsing. That is, in a single pass, the parsing as well as evaluation of the semantic rules. So these are the semantic rules we have written. Okay, these are the semantic rules we have written. But when they will be evaluated? Because ultimately this tree will only be constructed once this is evaluated. Just by writing these rules, this tree cannot be evaluated. This will be a kind of actual situation, or this will come into existence only when this is evaluated. So will this evaluation happen after syntax analysis, after the parsing is done? So it's saying it's better that you do side by side. So it's preferable that within the single pass, the parsing as well as the evaluation of the semantic rules are performed. Two categories of SDDs, or the syntax directed definition: the S attributed definition and the L attributed definition. The S attribute is actually only synthesized attributes are used in the syntax directed definition. So we're only talking about the synthesized attributes. So if we have an SDD that is only comprising of S attributed or synthesized attributes, that will be called as a syntax directed definition of S attributed types. And L attributed is the one, in addition to synthesized attributes, we may also use inherited attributes in a restricted fashion. Actually, we are allowed to use inherited attributes, but in a certain restricted way, not by any kind of logic. To implement S attributed definition and L attributed definition, we can evaluate semantic rules in a single pass, as we discussed in the previous slide. Implementation of S attributed definition are a little bit easier than implementation of L attributed definition. I hope if you can remember this fact when we were doing this evaluation of an expression in the previous lecture, then we were able to see that if all the attributes in a definition are synthesized, the evaluation order would rather become bottom up. So if you look closely, then the entire process of evaluation of those rules will become bottom up. We start from the leaf node and we move towards the root node. So that is definitely an added advantage. However, if we have an L attributed definition case and we have a mixture of inherited and synthesized attributes, so that does not guarantee a fixed flow of evaluation order. That becomes slightly random, moving from left to right, moving from top to bottom. So that becomes slightly more difficult. So it's pretty simple to say that S attributed definition, if we move work in this, its implementation will be definitely easier, because that's a unidirectional kind of a flow rather than the arbitrary L attributed definition situation. So if we talk about the L attributed case, so all synthesized, S attributed, good. If not all synthesized, then what can be the case? A syntax directed definition is called L attributed if in the semantic rules of the production of the type A derives x1, x2, x3 up till xn, the inherited attributes of xj, any component of this x1 to xn, any component xj, its inherited attribute actually depends only on the attribute, may be synthesized or inherited, of the symbols x1 to xj. So there is some xj, and its attribute value is dependent upon all the elements up till xj, excluding xj. So that's why it's saying x1 to xj minus 1. So this may be one of the cases, or the inherited attribute of the parent A. So any child is allowed to have the attribute value inherited from its parent or its sibling kept towards the right, or kept towards the left of its occurrence. So that is one restriction that has been applied in this case. So If this is the case, then this will be referred as an S attributed. So all S attributed definitions are also L attributed definitions. Let's just quickly review this this example. It's saying it's a non L attributed syntax related definition. Now I just want you all to be with me at this point and just try and see why is it saying that this grammar or this part A derives LM. Let's say we have this production A derives LM, we have this production A derives QR, and it's saying this is a grammar or this is a definition actually that is non L attributed. Now look, it's saying L dot I, that means there is some attribute associated with L and it is actually dependent upon its parent A. So this child's attribute is dependent upon the parent. Fine, I don't have any problem. So till now it's inherited and definitely cannot be synthesized. It's L attributed. So next one, it's saying M is actually dependent upon the attribute value of M is dependent upon its child. Its sibling on the left. So any xj will be dependent upon its child up till xj minus 1. So this is the second element, and up till the first element, any attribute value, if it shows a dependence, it's fine. So mi is dependent upon ls, it's okay. And this a, the parent, is actually dependent upon its child m. So this becomes a mixed case, that is, it's a synthesized attribute. However, if you look at the next production, which says the r, this is actually an inherited attribute corresponding to r. Its value is dependent upon its parent. Again, we don't have any problem, it's fine. And this q, its inherited attribute, it's dependent upon its child r. So now that this becomes a problem. If I do not have any doubt by saying that this is an inherited attribute. Why? Because one of the siblings actually its attribute value is dependent upon its another sibling. But as far as the L attributed case is concerned, dependence of M on L was fine, but dependence of Q on R is not fine. In this case, this might be inherited, but this is not the case of L attributed. So even though we can find many inherited and synthesized attributes, but this case of Q depending upon R creates a problem. So A dependent upon L or M, A dependent upon Q or R, everything is fine, but this one single case is actually spoiling the situation, that this Q is dependent upon R. Had this been the other way around, R dependent upon Q, we would have had no problems, I think, in considering this as an L attributed definition. So I hope you have got this point, that all the cases of inherited attributes will not be considered for L attributed syntax related definitions. Rather than for this lecture, we focus ourselves towards the bottom up evaluation of S attributed definitions. So bottom up evaluation, we have talked about LR parsers, we have talked about the SLR and the canonical LR situation, and if I hope you remember that they were implemented by the help of some shift reduce parsers, in which two operations used to happen. One was shift, that is shifting an element from the input tape to the stack, and the other one was reduce, was the time when we actually found that some portions of the top of the stack were matching the right hand side of any production, and that was luckily the right time when these elements which were matching the right hand side of any production should be replaced by the left hand side of that production by which it is matching. So we used to call that handle. So we said that we got a handle, and now we have to reduce. Replacement of RHS by LHS is reduce. So if you remember these 2 points of shift and reduce, then the things of evaluation of bottom up evaluation of S attributed definition will not be a problem. So we maintain the values of synthesized attributes of the grammar symbols into a parallel stack. Okay, now, so we have something called a parallel stack. If you remember the anatomy of the LR parser, we used to have an input tape, we used to have the algorithm, the LR algorithm, and we used to have a stack. That was one single stack, and that one single stack in case of LR was having both elements. It used to have variables, it used to have terminals, so both elements were existing on that. But now we also have something called the attribute value, so where that should also be kept. Now where to keep it? So not in that stack, we say that we contain a parallel stack. So if we are having Z, let's say this is the case, then we have Z dot Z. Let's say Z dot Z, this small z is the attribute value of Z. This small y is the attribute value of y. This small x is an attribute value of x. So we are containing corresponding things. So this is one of these. This is the stack of the parser, and this is the parallel stack that we have kept for the evaluation purpose of the definitions. So when an entry to the of the parser stack holds a grammar symbol x, any grammar symbol x, the corresponding entry in the parallel stack will hold the synthesized attribute of symbol x. Because during parsing we know that this is the production at which we are working, and once that production is over, we need to definitely apply. I mean, this should be the right time when we should apply the corresponding semantic rules also. So if we are saying we're doing bottom up parsing, we are evaluating in the bottom up situation, then if we have understood or if we have found out a handle and we now know that this production has been read completely and this is the right time to replace or reduce, then I think that should also be the right time to evaluate. This is what the logic is actually all about. So the evaluation of values of the attributes are done during reduction operations. This is very important. So whatever attributes we are trying to evaluate, this will be done only during those reduction operations, not during the shift operations. So A derives x, y, z. Let's say this is the production that we had, and luckily we have x, y and z kept onto the stack, and also luckily the table, the LR table is telling us that this is the right time, the handle is there. This is the right time, replace this x, y, z, pop all these elements out and replace it by A. Okay. So once it is telling me that this is the right time to reduce, it's actually hint also that this is also the right time to evaluate. So in the parallel stack we are having their corresponding attributes. We may have multiple attributes at the same time, and after reduction we expect the answer to be something like, or the configuration to be something like this. That is the elements x, y, z have been replaced by A, and all their attributes have been replaced by the new attribute A dot A. And if this is S attributed definition, then this attribute A should be dependent upon Z, Y and X, or X, Y, Z. This is what it is being said over here, that if it is an S attributed definition, that means all the attributes we are talking about should be synthesized. Then the attribute of A should be dependent upon its children's attribute X, Y and Z, as being shown over here, that this A is actually dependent upon as a function of X, Y and Z, where all the attributes are synthesized. So this is what the idea is all about. When you reduce, this is the right time that when you should also evaluate. A syntax related definition is S attributed if all the attributes in size. Dependency graph can be observed to be a directed tree pointing upwards. Upward means towards the parent, and all of them when observed together will be actually pointing towards the root node. Towards the parent at each subtree, this can be evaluated in the bottom up fashion. This technique is consistent with the bottom up or shift reduce parsing, possible to do evaluation of the attributes using the stack at the time of reduce operations. So we are already having a stack. We just have to maintain one parallel stack, and these two things when they get together as far as the reduce operation is concerned, then this evaluation seems pretty much possible. So suppose the stack of a journal shift reduce parser has the following contents. Dollar is the end mark of the stack, x, y, z. The grammar symbol A, x, y, z have the attributes. We've already done this example. So it's simply saying that after the reduce operation, A derive x, y, z, semantic rule this, the new stack content will be A, and this will be the value of its attribute. So it's more a descriptive thing of what we have just talked about. So let's just talk about an example of what we are trying to say. If again we are talking about the same grammar, it's better to stick with one, and we are having those same semantic rules which were actually evaluating the value of some expression. So let's say of this we give a more detailed situation, that L derives E derive E plus T, E derive T derive E star F, and we are saying a more detailed description that print whatever value is there at the top of the stack. Top actually refers to top of the stack. Val n top, this is the new top actually. Val top minus 2, val top. We are talking about an expression. An expression will only have two elements. So that is why we are having the comfort of directly saying top minus 2 and top. So the first element, that is the top, and top minus, that is the second element. So val top, and so this is the way we are moving around. So let's say this is the definition that we have corresponding to this for the purpose of evaluation. So top refers to the top of the stack, n top is the new top actually after popping the right hand side of the production, and val actually contains the attribute value of the stack contains. The new top actually is top minus r plus 1, where r is actually the right hand side of the production. We'll understand what we're trying to say. I hope if you remember that that reduce operation of LR parsing, it said whatever number of elements you had in the right hand side, twice those elements should be popped out. If you talk about SLR, CLR and LLR, twice the number of those beta, A drives beta is the production, then twice the number of beta elements should be popped out from the stack, and A should be pushed in. So if you're not talking about the states in specific nature, then we can simply say top minus R will be our new type. So originally we were having, let's say, 5 elements, and now 3 elements have been subtracted from it. So the new top location will be evaluated in this way. So this is the very way we have been checking the sentences from a grammar. So just to see over here, stack, input and action, we did this earlier as well. So this is the stack, and we are also actually containing the corresponding attribute value. So dollar, so this is a sentence. So initially we had what, 3 star 5 plus 4 n dollar, that's the end mark of the sentence. So the table, I mean this part is actually coming from the table. The table is telling us right time to shift. So we shifted. We shift over here, and I mean we're also having the corresponding production or the corresponding component from the grammar. So digit comma 3, and then it say this is the right time to reduce. So we replace this element, and this goes on. We'll simply move ahead and we'll try and understand this part a bit more in details. So we're talking about the same example, E drive E plus T, E drives T. We'll just take, this is the canonical LR0 set. We won't go much into it right now. We've already done that in the parsing process. Okay, so let's take a proper example. Let's say we have a sentence 1 plus 3 star 4 R. R refers to, let's say, the print operation. So initially the stack was having, let's say, state 0. So you need to recall those state the parsing components. So this one thing actually is being added over here along with this val stack. So you're having 2 stacks now. This is a stack of what your LR parser was saying, and this is a stack where your attribute values are being kept now. So no attribute right now, state 0, you get a 1. So the action from the table is actually coming S6, let's say. So we do not need a table right now, this action part is already telling us. So S6 we have, that means shift this and put a 6 over here. So we shift this, we get a digit actually, and this digit has been replaced by 6, because actually 1 will not be shifted directly. 1 is actually coming from that grammar. This is what I wanted you to understand. This is actually coming from the grammar digit number. So this digit has been kept over here, 0D6. Now the attribute value at the val stack is 1. Okay, so now we have plus 3 star 4 R. We definitely would have been having a table, and this table is telling us that on state 6 under column plus you should have F drives D. So nothing is happening actually. We simply move on. So this action F derives D is corresponding having, I mean, do not do anything. So we'll have to be consistent with this. Okay, so no specific operations, simply transfer of values. And 0D6, this now a new state has been, so this was actually a reduce operation, FD, F derives D. So we have got a D, this has to be replaced by F. So these 2 elements were popped and were replaced by F, and then 4 came onto it. I mean, this again, the answer, if someone thinks about how did we get this thing, one has to recall the syntax analysis process. So we are having this was a reduce operation. So we have it back again, 0 F4, now 4 comma plus. The table is telling us that this is the right time to reduce F by T. So we can see T now over here, and on top of that T we are getting a 3. This 3 must have been coming from the table again, the go-to part. So now we are having the configuration 3 plus, so that gives us an answer of E drives T. This is again an answer coming from the table. So we replace this T by E, and the new state on top is now 2. The val stack is not changed anyhow, it's still having the same thing. So this is 2 and 2 comma plus, the answer is now S8. S8 means shift. So E2, this plus as it is has been shifted over here, and this has been followed by state 8. So we getting 8 comma 3, we get S6. So we are continuously applying them, applying these actions. These actions are actually coming, this has nothing to do with syntax semantic analysis actually. This is coming from the table, of semantic analyze, of the syntax analyzer, the LR parser, maybe SLR or CLR. So it's coming from that very portion. So this goes in here, and slowly and steadily we'll see that these val stacks are also getting filled up. So if what I want you to draw your attention to is actually, you can see some semantic actions also taking place. Okay, so it's saying at this portion it said do nothing. It was simply e f dot val equal d dot lex val. Look, this was a semantic action. So it's simply pass on this element to this. Do not do anything new. Do nothing means do not do anything extra. Do not evaluate anything further. Simply pass on these values. So at all these locations, you are also telling what semantic rules are being performed. If we have been doing only syntax analysis, I would have been talking about this part, and this part. But we are also doing semantic analysis, so we have added 2 more parts to it, 2 more columns to it, the val stack and the semantic rule part. So you can see that all these operations are not being performed at this very level, at this very point. Now it says T, because this operation is being performed, this production, T drives T star F. Till now you can see all those F drives ID, T drives F, all those simple ones were being operated. This production has come into picture now, T drives T star F. It means 2 things. One thing is that this entire T star F is present on the top of the stack. We can see over here T star F. As far as syntax analysis is concerned, we have found a handle. This all will be replaced, this all will be extracted and be replaced by capital T. So this is one part of it. So entire T star F should be replaced by T. We can see over here entire T star F will be replaced by T. A new state 11 has been put onto it. But semantically this also means something. It means that 2 elements on top of the val stack. Now what comes on top of the val stack? 3 and 4. These 2 things are there on top of the val stack. So this 3 actually refers to T1 dot val, this 4 actually refers to F dot val. It's saying pick up these 2 elements, multiply them, put this operation, and you put this into this new attribute T dot val. So in your in your stack you are having T, capital T, and in your val stack now you should be having the value of T star F, that is to be held by this T. So we are having 12 over here. So this 1 actually refers to the attribute value of this, and this 12 actually refers to the attribute value of this T. And now you can see that the table is telling us this is the right time to reduction of E plus T by E, and we can see that we have E, we have plus, we have T on the input stack as well, on the stack as well. So this entire E to everything will be replaced by only capital E as mentioned by the production. So E plus T replaced. And also this is also the right time for us to evaluate our semantic rule. Look, our semantic rule is also there. So this semantic rule is actually telling me that this first value or the top value actually refers to T val. This next top minus the second location value is actually referring to E dot val. So you multiply these 2 values and you transfer the value to E val, which is actually now being kept on the stack as well as its attribute values kept on top of the val stack. So this was a plus. So I had 1, I had 12. This should be added. This should be multiplied. This should have been a plus operation over here rather than a multiply. So E plus T. So this should have been 1 plus 13. This answer will go to E dot val, the one that is being now situated on top of the stack. So you can see a 13 being kept over here. Again, the shift operation is happening and so on. But we could see that. Now the semantic rules are also being executed exactly at the right time when a particular production has been successfully told to be reduced every time. So reduction operation, a semantic rule happening. We could not find any change actually in the val stack. No change in the val stack. Do nothing means not much change in the val stack. But still a semantic rule is being performed. Every time we reduce, a semantic rule being performed. Every time we reduce, a semantic rule being performed. No change in the val stack. On a shift operation, no change in the valve stack, no semantic rule also being evaluated. So at all the shift, no semantic rule being evaluated. It's simply a shift operation being happening. A semantic rule being evaluated only when we are actually reducing. So we got this we got this correct actually, that as far as the bottom up evaluation is concerned, the right time to evaluate any semantic rule corresponding to any production of a context free grammar should be when this production is the target of any reduction operation. So if you are about to reduce for a certain production, that should be the exact right time when you should also evaluate its corresponding semantic rules. Till the shift operations are happening, you simply pass on the contents of the input to the stack. And you also have to maintain the val stack as well in this case, because the values of the attributes will now be kept on the val stack. The grammar symbols will be kept on the normal stack, the stack that was associated with the parser. So we have to now broaden our perspective as far as the semantic analysis and parsing is concerned, that this is the parser stack and this is the semantic analyzer stack, and they both go hand in hand. Something happens in this, some change happens in this, you reduce over here, you also perform some operation over here. So this makes our evaluation pretty much simple. Okay, so to conclude today's lecture, we talked about some syntax trees and their constructions. We also talked about the concept of directed acyclic graphs and how are they beneficial in helping us in generating optimal codes. We talked about S attributed definitions in grammars and L attributed definitions in grammars. We discussed about the process of evaluation of semantic rules, and definitely we talked about the bottom up evaluation of the S attributed grammar. For references in further study, we can, as I said, that I have been following this compilers, principle and techniques and tools by Alfred Holman Sethi, as well as Monica Slam, and also another good book by K.D. Cooper and Linda Toxon on engineering a compiler. Thank you.
With this note, thank you, sir. Thank you so very much for giving us such a productive session. Dear friends, if you have any queries or if you want to give your feedback, you can mail us at info.cc@nic.in. And if you wish to see this particular lecture, you can see it with the help of YouTube. As we really say that we upload our lectures on YouTube so that you can access these lectures ample of times. With this note, thank you, sir. Thank you so very much once again.
Thank you so very much.